Hello, AP Statistics. This is section 12.1, Inference for Linear Regression. For many of you, this is your last section of this course. So congratulations for being done. You will need a t-distribution table, graphing calculator, pencil, paper, note sheet. Once you got those things, you'll be ready to go. All right, so here's what I have. First story problem for you. Natalia Del Sante is your typical All-American softball player who's played softball since she was a toddler. She believes her time spent hitting softballs in the batting cages has a direct influence on the total number of hits she has in her softball games for the respective week. The chart below shows data from random samples of weeks where the total number of hits she had in her respective games were recorded based on the number of hours she practiced in the batting cages for the respective week. Random hours of batting cage time in the batting cage per week were inputted in numerical order within this table. Okay, so, and again, this is just a sample of 19. If you consider 52 weeks in a year times many, many years that she's played, this is just a small representation of her hours in the batting cage per week. And again, the number of hits that she has in respective games for that same week. Okay. Now, first thing I'm going to ask you is, what is alpha? That's this guy on the bottom here. What is beta? And what is sigma? What are those things? Okay. Well, when I think about information that's given, okay, oftentimes I associate that with a least squared regression line, which comes in this form. Okay. Now, this sample of data is good for a representation for this A that I have in my equation and my B. Okay, and again, that is good for a sample. Okay, however, if I had a population of data, okay, where I considered every single week that she's played softball, okay, we'd have to suggest that that's really hard to find. Okay, I can't get records of everything that she has done and place them on this screen to get a, I guess I'll say, a population representation of her vertical intercepts and a population representation of her slope. Okay, because again, 52 weeks a year times, I don't know, 12, 13, 14 years of play just leaves up a lot of values, okay, for hours of practice and the number of hits per week during her games. Okay, so because those are too difficult to find, okay, in terms of population sense, we use again this linear regression equation using A and a B. Okay, had we been able to use a population representation, okay, instead of having an A, we would have an alpha, and instead of having a B, we would use a beta. Okay, so these are used for a population, which again are usually too hard to find. Population data. Okay, and so what do? We use our sample data to help kind of estimate what we think that true population data may be. Okay. Further, we have a sigma here. Okay, and this also represents a population. This is a population standard deviation. Okay, again, usually too difficult to find. So what do? We use a sample standard deviation, and I have this box with an S off to the bottom right. Okay, and what this tells me in context of the story is, again, a sample representation of basically the standard deviation of your residuals. Okay, so this is a standard deviation of your residuals. And you're like, okay, what are residuals? Well, if I were to take all these data values, okay, and plot them, let me put a big item on the top here and just plot, I'll just plot a couple points. Okay, and draw a least squared regression line. Okay, the vertical distance that each of these data values have to your least squared regression line is a residual. Okay, and how far on average those data values are from the least squared regression line will be what my S is representing. Okay, if I could do that for an entire population of data, it would be sigma. Okay, but again, that's too difficult to do, so I will use S for my sample to help estimate what I think this sigma to be. Okay. All right. Now, how do we find those calculations, those estimates? Well, it's work that we've done in the past. Okay. Again, because we usually recognize our alpha and beta in terms of A and B, we usually see it in this context. Okay, y hat equals a plus bx. Again, we typically define x and our y hat off to the right. Okay, and so what I'm going to do is I'm going to use this information, put it in L1, put the second row of information in L2, and do a find the equation for the least squared regression line. Okay, so if you don't remember how to do that, I'll put some directions underneath this first screen on the bottom left. You go to stats, you'll go to calc, and you're going to hit 8, which is Lin Reg a plus bx. Okay, you'll put your L1 in there, you'll put your L2. I like to store my Y1 in that position as well. Okay, I think most people are used to doing that, at least in my class. If you're not sure how to get the Y1 there, all you do is you hit alpha, trace, okay, and usually the Y1 is an option for you to choose. Okay, and then once you select that, you end up with this set of answers. Okay, and so I oftentimes just out of habit will write those in. I'll say y hats is equal to 0.6989 plus 1.9177x. Okay, and then I can describe, of course, x and y as well, which we will do a little later, but that doesn't really answer my question. Okay, the question says, what is alpha and what is beta? Okay, and since again, I can't find population data, I will use my sample data for estimates. Okay, and so what I'll say is that alpha is 0.6989 and my beta is 1.9177. Okay, now some students will ask a great question. They'll say, hey, isn't alpha our significance level? Isn't that what our alpha cutoff is? And whether we decide to reject or not reject based off this cutoff, it typically is. It actually has a double meaning, okay, within this work. So for now, I'm just going to say this is an estimate for your y-intercepts, okay, your vertical intercepts. However, this is not your significance level as well, okay? Your significance level will be determined in the problem, or you just may assume it's 0.05, okay? But this is not a significance level. This is again, your vertical intercept. I'm just going to abbreviate that. Okay, so we found two of the things. Here's your alpha, here's your beta. They're pretty easy to find once you put your items in your L1 and L2. Okay, so what do we need now? We need S. Okay, and S is an estimate for the true population parameter of the average distance that your data values are vertically from your least squared regression line. And so what I need basically is I need some residuals. Okay, and I'll use my sample here. And my formula, okay, for S goes like this. I'm going to handwrite it out. I don't know why I didn't print it out ahead of time, but it's 1 over n minus 2, okay, times the sum of the residuals squared. Okay, so if you're not remembering how a residual is found, okay, it's all your observed values. Let me write this over here. And when I say observed values, it's your observed y values. Okay, minus your predicted y's. Okay, and I usually like to identify predicted y's with my prediction equation, which is y hats. Sorry if that's hard to read, y hat, with your respective x value inputted. Okay, and then these are the y's that we found from your actual data. Okay, so it's the data values that you have basically in your L2. Okay, you have your y1 stored, your prediction equation stored in y1. Okay, and then your x's are all in, again, L1. Okay, so again, it's your y's minus the predicted y's for the respective x's. Okay, and in terms of calculator syntax, it's L2 minus y1 with a hat on it, which is where your equation is stored. And this is not times, this is an input set of parentheses with an L1. Okay, when you do that in your L3, and you can see how it's typed at the very bottom, if you look at this very bottom of the screen, that's how you enter your syntax. Okay, you should end up with these values. Okay, now that's just part of the formula. That's this piece. If you can see what I'm kind of bracing as your residuals, I now need to square it. Okay, and so what I'm going to do is go to my L4. And in my L4, I'm just going to write L3 and square those. Okay, and so your new screen will look like this. And again, you can see my L4 is highlighted. Make sure you highlight the title. Okay, and then you have L3 squared. Okay, so once you square those, okay, then we'll identify this part of the formula, which is the sigma, and we will add everything up in L4. Okay, and so again, you just go to stat. I'm typing this or handwriting this in the box here, stat, go to calc, this is the very first thing, 1var stats, and again, we're going to input L4. Don't forget to type the L4 in there because the default's usually another list and you're going to get the wrong sum, okay? And so when you get that, the sum that you see is not, it's not this one. I'm going to scratch this out because I don't want you to put that in there. It's not the sum of the squares. You already squared things in your L4. Okay, but it's this sum right here. So I'm going to put a big square root bar. Okay, and that sum is 13.25999. I could probably just said 13.26, but I got on a roll there. Okay. And again, out in front is 1 over n minus 2. And you're like, what is n minus 2? Well, n is the number of coordinates that you have. So in this case, my n is 19. Put this kind of underneath me. And if I subtract 2 to that, n minus 2 is 17. Okay, so I'll put this right in there. Excuse me, let me put that in right. 19 minus 2, which will give me 17. But I'll give you the unsimplified version right there. So 1 over 17 times 13.25999. And again, let me rewrite this if you can't see it. Gives us 0.88317. Okay, 0.88317. In fact, I'll even put a 6 on it because it didn't round well. There you go. All right, and so what does that mean? That's how far on average your data values, okay, in your sample are from your least squared or regression line in a vertical sense, okay? So there you go, and that means that is an estimate for what we believe sigma to be right underneath it, okay? All right, as we move on, I'll just tell you that S is the hardest part of today's lesson, okay? So if you can kind of grunge through that, then the rest of this work should be easy, okay? Next questions you'll see often in your homework, it'll say find the least squared regression line, and you just did it, okay? It was on the previous page. Let me see if it's still there. Yeah, it's this guy. Where's my marker? There it is. Okay, and we want to describe what X and Y are, so I'm just going to move over here. I'll hit enter. We already had this information that helped us find this answer. And there you go. Okay, Y hat is equal to 0.6989 plus 1.91774. Again, this is your A, and this is your B. Okay, and again, of course, I always define my X and my Y hat. Okay, now the second part, most people know what slope is by the time they hit AP statistics, but we want to make sure we write it with good context, okay? And so remember, the way I describe slope is first by looking at my B, and that is 1.91774 over 1. And remember when we first think about when we learned slope a long time ago, most people describe that over as the change of Y over the change of X. And so when I write a description for slope, I usually talk about the bottom piece first. Okay, I'll say for every 1 unit of X, which is hours of batting practice per week, we would predict, and that's an important word, predict, well, because this is positive, an increase of Y, which is the number of hits per week during games. Okay, so let me address that, and we'll write this out. Again, for every 1 hour of practice in the batting cages, this is my X, okay? We predict, notice that this is in all caps and it's also in red because that is a huge item that's looked for amongst AP grading, okay? We're not guaranteed that you're gonna have 1.9177 hits for every hour of practice, it's just a prediction, okay? Again, an increase of this value, okay? And of course, we use the word increase for this, what I'm going to call Y, because it was positive. Okay, your B was positive. If your B were negative, then you would say decrease. Okay, but then that's the case. Make sure if you wrote decrease that you don't put a negative with it as well. Okay, so make sure you include the right word, increase or decrease, and then write the absolute value of whatever that B may be. Okay, and again, don't forget this magic word here, predicts. That's an important part of our story. Okay. All right. Now, some things that were included on this new screen, okay, is the information that we had from the previous one with respect to our least square regression line and the math of how we got that. And here's what they ask. They say, is there evidence that Natalia's numbers of hits per week increases with increased hours of practice at the batting cage per week? Okay, and then they give you a little bit of information past that. And when I see this, is there evidence? That means we're going to have an inference test, okay, with a null and alternative hypothesis, and need all 5 steps to get a good conclusion at the end, okay? All right, so this one has a little bit different features compared to the other ones, even though 5 steps still exist, okay? But the first is the null and the alternative hypothesis, okay? And unlike other ones, we're not talking about proportions, okay? So there's no p's in our null and alternative hypothesis. There are no averages, okay? So we're not going to have mu's in our null and alternative hypothesis. And last chapter was with chi-squared, that's unique in itself. This one, we're talking about slope, okay? Is there some type of positive relationship between the hours of practice that she has in batting cages per week and the number of hits that she has in the games for that respective week, okay? And since I'm looking for that kind of like that explanatory response relationship, you know, is there some type of positive relationship there? I'm going to look at our slope. Okay, and so if you look at my null and my alternative hypothesis there, okay, I have a b is equal to 0 and a b is greater than 0. Okay, it's a greater than sign because we do believe that there is a positive influence, positive representation in terms of, again, her hours of practice and her number of hits per week during games. Okay, but I will define that right here, what b is for both of those. Again, that's the population slope relating to the hours of practice at batting cages per week to the number of hits during her respective games. Okay. Again, this B is usually too hard to find. Okay. I can't include every single data point for a week's worth of practice and games played, number of hits for the games played for the past 14 years. It's just too hard to do. Okay, so again, we had to use our sample to help predict what this may be. Okay, now, with this, okay, comes conditions. All right, and when you think about conditions, the book cleverly uses this acronym. Okay, and we'll go with that as well. Okay, now some people will ask, do we have to memorize this? It's like, you'll have to know how to do it for your problems, okay? It is very involved where, in my honest opinion, okay, and it's just an opinion, it would be very time consuming to do all this for a free responsive question on an AP test, okay? It wouldn't surprise me if such a question were to be presented to students that they may see your conditions already satisfied, but nevertheless, we'll still talk about how those are done. Okay, the first one is linear, and all I want to know is from my original set of data points, does it form, does my scatter plot form a line? Okay, so I'm going to look at 2 things. You're going to notice 2 graphs that pop up. One is my least squared regression line that will pass through all my data points. To me, this looks good. okay? And further, okay, I'm gonna look at the residuals, okay? And this to the right, even though it's gonna satisfy a different type of test, are my residuals. And you'll notice that those do not make any type of smooth curve, okay? And so between those two, I think we're good, okay? So it does look like those data points do make a good line. And residuals, I'm just gonna write over here, okay? No smooth curve. Okay. Independence, okay, relates to our 10% rule because I did not replace my data values that I got for her respective weeks back into the original pool. We had to do a 10% rule. I consider all of her games that she's played during the last maybe decade and a half, and all the weeks that she's played, she more than satisfies this. Okay, so this would mean that she needs at least 190 weeks. Since there are 52 weeks in a year, and she plays weekly with her club team, etc., she's more than satisfied this. Okay. Normal. Okay, like what does normal mean in context to your least squared regression line? Okay. Here's what I have. Okay. These are just your basic residuals. Okay, the values of your residuals. Okay, and so if you were to create take your L3 basically and just plot your L3 where this is 0 and it's going out to the positive direction and go to the next one. I think these are each 0.5. Okay, this is 1.0, 1.5, etc. You'd find that if you were to do some type of histogram for the number of values in each of these, it does look normal. Okay, so this is a good representation of residuals. Okay, in terms of distances. Okay, from the predicted value from the observed values. Some of them are very, very close to 0, which is what we want, and then there are others that are further away, but not as many. Okay, and again, these go out in the negative direction, negative 0.5, negative 1, etc. Okay, so that one is satisfied. Okay, equal standard deviations. Okay, I abbreviated standard deviations because it did it in the book. And so what that means, if you look at it from beginning to end, okay, and again, this is nothing more than your residual plot, you'll notice that some of them are super tight to 0 here, and some of them are a little bit more extended, some of them are super far away. And the fact that you go from left to right and there's a good balance of, I don't know, small distances and large distances means that that we're good, okay, that this is satisfied. We don't see a bunch of tight distances in the front and then have it get bigger and bigger and bigger as you move to the more positive direction, okay? You have small residuals and large residuals from left to right, very balanced as you move through, okay? The last thing is random, and we have to ask ourselves, were our 19 data values randomly selected? And I'm going to say yes, and you'll notice that something will pop up on your screen. This is from the original problem. It's in green. I'm going to highlight it again in red. We said in the very beginning, this is a random sample of weeks, okay? And it was stated, so our conditions are satisfied. Okay, so we have step 1 and step 2 done. Okay, we have our null and alternative hypothesis. We have our condition satisfied, and now we are doing our test statistic. Okay, which is T is equal to B minus the population beta. Okay, now our population beta is basically what's in our null. Okay, kind of like what we saw in our previous examples in previous lessons. And I'll just share that most of the time, beta will be set equal to 0. So most of the time, you won't even see this back piece here, though it could exist. Okay, and so I have beta over my SEB. SEB, if you are not sure what that is the standard deviation of your slopes. Okay, now there are many, many samples that could be of size 19 that we can take from our population, okay? And our sample slope may be a little bit different from my population slope, okay? Had I picked another group of 19, I may not get a B that's exactly 1.9177 like I have right up here, okay? It could be that another sample of 19 would give me a little bit different slope, okay? And so on and so on and so on. So every group of 19, every random sample of 19 that is picked will have a slightly different slope, okay? The standard deviation of those slopes, okay, or how far on average those are from the, I'll just say the population slope, okay, is your SEB. Okay, so I'll say with respect to population slope. Okay, so again, how far on average your sample slopes are from your population slope. Okay, and so again, most of the time this will be 0. That's the only reason why I'm crossing this out. It's not that it shouldn't be there. It's just that usually it is this guy. Okay, so whatever's there goes in this position. Okay, and so I have B over SEB. Okay, and SEB is defined as S over this value right here. Okay, which is variation of the, it's like the standard deviation of your x's, basically. Okay, degrees of freedom is n minus 2. Why do we have degrees of freedom? Well, it's because we're dealing with a t distribution here. Okay, and so if I input values, okay, again, we agreed that our beta was going to be 0. 1.9177 is the b that we have at the very top. Okay, standard deviation of standard error of the B, again, is S over this mini formula, okay? And your S was that monster thing that we did on the previous screen, okay? So your S is right here, 0.88318. We just did that, okay? And some people are like, how do you get this guy? Well, luckily for us, they provided it for us, okay? But it's basically a form of a standard deviation of your X's variation of it, okay? So we will put that down here, okay? Do all of our work. It's pretty easy math because we've done all the work to get all these small pieces, and you get 15.511, okay? With our degrees of freedom of being n minus 2, n is 19, subtract 2, you get 17, and you can do a TCDF to get your p-value, okay, which is basically 0. All right, now, what does that mean? I think our alpha cutoff was pretty small. It was 0.01, and 0.01 is a small alpha cutoff, but we had something even smaller. Okay, so be careful of this guy. I think you know this by now. Usually they have an E in your problem when they answer this for you on your graphing calculator, and we don't write E there. We do write this times 10. Okay, or at this point you can just write 0, and we're good with that. Okay, what does this mean? Well, we can write a conclusion here. It says there is evidence to suggest, okay, because we have to reject the null that was already stated right above that. Okay, there's evidence to suggest. Notice this part in green is just the part that I had up here. Okay, you're always reciting what I call the ha. Now the ha starts off with the B, so I just recopied that. The population slope relating the hours of practice at batting cages per week to the number of hits per week is, and what am I saying here? It's greater than 0. Okay, so so that is basically done. All right. Now, with every problem I provide, people will ask, isn't there a graphing calculator way to make this go pretty smooth? And there is. Okay, so let me show you really quick. If you want to go to stats, okay, and then scroll over to tests, instead of going down, go up, okay, and it's F here. Okay, it's linear regression t-test. Okay, and if you want to copy that command down, TID4 Lin Reg t-test. Okay, this is what you'll get on your screen. Your L1 and your L2 is where you have your original data. Make sure you change this to a greater than sign for this particular problem. Okay, it's wise to plug in your regression equation again, okay, because you'll find that you'll use this a little bit more. Okay, so just hit alpha trace. okay, right in there. And you'll find that it'll offer you the opportunity to put in your Y1. Then you hit that calculate button and you should end up with this, okay? Again, all you have to write is TI-84, Lin Reg, t-test. Okay, notice the things that it has here. It gives you the T, exactly what I had before. I'm going to box that. Okay, it gives you the P, which is exactly what I had before. Okay, which we'll just say is 0. Degrees of freedom we knew. There's your A and your B. So it actually does that Lin Reg A plus BX command that we did earlier. But most important, let's notice what else it does. This is the second to the last thing on the bottom here. Okay, sorry, this is the last thing on the bottom. It's before you scroll down, it gives you the S. Okay, so for that pain in the rear S that we found on the previous slide, it'll give it to you right here. Okay, so you don't have to do all those steps. However, in the end, we kind of have to anyways with our conditions because we need to know what a residual plot looks like. Okay, so does it escape us from actually having to find an S for that actual calculation? It does, okay? However, you still need the residuals for that within your L3 to do your conditions, okay? As our second step of this hypothesis test, this inference test, okay? All right, last question is this, and we talked about both of these. What is the difference between sigma and SEV? Remember, sigma is the standard deviation of your residuals, okay? And then remember, SEV is the standard error for your slope, okay? So when you consider all the little b's that you can get from samples of size 19, it's about how far on average those are from your true b, okay? Your say your true b, but your beta, okay? All right. If there's nothing else, we'll move on to our second problem. This one will actually go quicker. That'll surprise you. Part of the reason I'm just going to jump to this last sentence here is to assume the conditions are satisfied. Most people glow when they see that, but here's what's going on. Mr. Castillo owns a big house with a huge yard. Each day of the month of April, Mr. Castillo's wife counts the total number of weeds for each square foot plot within his yard. Okay. For the month, a random sample of 30 plots from varying days were chosen where the total number of weeds were per square foot were counted based off the number of days since April 1st. Okay, and this is the mini tab output. Okay, now we've done this before. Okay, so if you remember, this is your A and this is your B. Okay, so if you want to write a least squared regression line as they're asking for here, then it's really easy to do. Okay, this will be your A, and this is your B. Notice behind there, I described X and Y. X is the total number of days since April 1st, and Y, which is predicted, is the number of weeds per square foot for the various plots that are found during that respective month. Okay. All right, now from there, it says describe the slope, okay? And remember again, it is the change of y over the change of x, okay? Y in this context is what we see right here. I'm gonna just highlight that. It's the total number of weeds, okay, per square foot. And this on the bottom is number of days since 4/1. Okay, so that's a 1, sorry. I can describe that out, and I usually go from the bottom, okay? It's 2.064 over 1. And so for every 1 day past April 1st, we can predict an increase of 2.064 weeds per square foot in Castillo's yard. Okay, so again, don't forget the word predicts. This is my X, this is predicts, and it's an increase because again, your slope is positive. Okay, cool. All right, next question. New one to us says find a 99% confidence interval for the true slope of B, where there are 30 days in April. Sorry, that doesn't hold too much significance, with a degrees of freedom of n minus 2. Okay, so there are 30 days. The big thing is that our n is 30. Okay, we'll talk about that in a second. First thing is we're going to describe B. Okay, and this is up in the top left-hand corner. I just put it up here so you can see it. In the place where I sometimes have room. But yeah, remember that beta is the population slope relating days since April 1st to the total number of weeds per square foot. And the conditions are satisfied. And I boxed this thing green here. We talked about that in our previous slide. Okay. Your confidence interval, okay, is B minus this big B, okay, the big beta. But again, we're going to assume that it is a 0 here. It's not going to have any significance. All we want to do is to show there is a positive relationship in some sense. Okay, your degrees of freedom is n minus 2. So 30 minus 2 is 28. Okay, and again, we got that 30 because there were a random sample of 30 plots. Okay. All right, so what is our B? We know what B is, it's right here. Our SEB, okay, I'm skipping the T just for a second. SEB, you're like, oh man, standard error B, how do I find that? That is actually, if you look at the next column over, it says standard deviation. This over here is SEB. That is the standard error of B. Okay, and so what does that mean? Well, if I put in my value for B and put in for my SEB, the only thing I need left is my T. Okay, and how do you find that? Well, you use your T distribution table. Okay, and I don't have a copy of it now. I know you used it enough to have one with you. Okay, and again, we have 99% confidence interval. So you'll have to check that on usually along the bottom row. Okay, and then you'll scroll up to a degrees of freedom of 28. Okay, and if you do that, you'll find you have that 2.763. Okay. And so what does that mean? Well, if you were to do that math, okay, you would get 0.3139 and 3.814. Okay, that is the plausible values for 99% confidence interval for our beta. Okay, which is again the population slope of again the number of weeds that you would expect in a square foot plot per day since April 1st. Okay, and what do I need to do? I just got to take these numbers and make a concluding sentence here. And we'll say it like this. It says we are 99% confident the interval from 0.3139 to 3.814 captures the true population slope for the number of weeds per square foot for each day since April 1st. Okay. So there you go. There are definitely 3 steps just like before. Okay. How do you find a confidence level? Remember, they kind of work themselves out like this. They're all kind of the same. For many repeated samples of size 30, 99% of the resulting confidence intervals will contain, okay, the true population slope B for, in this case, the number of weeds per square foot for each day past April 1st. Okay. Pretty much all of our work is the same except for the context, which is in this very back piece. Okay, but the stuff in front of it is usually pretty standard. All right, we will keep going. Okay, and notice it's the same table, and it says, is there evidence to suggest? Ooh, evidence to suggest means that this is going to be an inference test where we'll have a null and alternative hypothesis that the number of weeds continue to produce as days go by. So if I say continues to produce, that means that we have some type of increase. Okay, and if we're increasing, what does that mean? Well, it means that again, our beta must be bigger than 0. Okay, where again, just like from the previous slide, beta is the population slope relating days since April 1st to the number of weeds per square foot. Okay, conditions, okay, are satisfied. Okay, that was stated before. And then we have our T. Okay, remember T is equal to B minus the big B, which is beta, all over SEB. And so here's the deal. there's your B. There's your SEB. Okay. And most people know, hey, by now, B over SEB will help me find the T. Okay. And you can divide those out. I know you know how to do it, but notice this next column, the one that's off to the right here. And B over SEB is 3.26. Okay. And if you divide those out, just like you think you would, this divided by this, as you see right here, okay, it does give you 3.26. Okay. All right, now what do we do with that? Well, we'll take this and we can do a TCDF just like before. And some people will notice, dang, we have p-values over here. Is this my answer? Close, okay. Unfortunately, when you have a Minitab report, it can't tell whether you have, for your null and alternative hypothesis, either a greater than sign, a less than sign, or a not equal to sign. Okay, so what happens? They assume that from this test, it is a not equal to sign. Okay, which means if your original intent was to have a greater than sign or a less than sign, you'd have to take this and this answer basically and cut it in half. Okay, and if you actually did a TCDF, you would find that it would actually give you this. Okay, so if you were to do TCDF and put the ratio in, the T ratio, and then say maybe 1,000 there, and my degrees of freedom, which is 28, okay, you would actually get this bottom one, okay? And the reason why is because this is a one-sided test, a one-tailed test, whereas it is assumed, okay, based off this Minitab report that it's a two-tailed test. And so if they give us data for a two-tailed test in the end, we got to cut in half to represent a one-tailed test, okay? All right, last piece of information, and I'm going to cut out one piece here. I repeated something. 2. There we go. I have some extra stuff. Is the correlation coefficient and the coefficient of determination. Okay. If you're not sure which one is which, I know people say, oh, one is R and one's R squared. This, of course, is R. They don't typically say what is R in your questions. They'll actually give you the vocabulary word. This is coefficient of determination, which is R squared. And you'll notice that in your problem, it does give you on the very bottom row of your Minitab report an R squared and an R squared adjusted. Okay, which one do we use to help answer this question? Take this away. We don't want the adjusted one. We'll use the R squared. So coefficient of determination is 87.6. There's no calculation for it. You just write it down. Okay, you may want to say 0.876 if you want. Okay, but it's totally up to you. And then to find the R, what you're going to have to do is take your R squared. I'm going to put this right in the middle. R squared equals 0.876. Okay, and then square root both sides. Okay, and make sure it's not in the percent form, 0.876, and we get 0.9359. Okay, and so now some people may say this. If I square root both sides, isn't this a plus or a minus? And that is true. And I don't really want to write both. How do I know which one it is? If it's the plus version or the positive version or the negative version? Most students will figure out that it is actually determined by looking at your slope. Okay, so I'm looking at my B here. I got a big star next to it right now. Okay, B is positive, so I only want the positive version of it. Okay, so that is what my R is. All right, that is it. Some of your work will be written in Minitab form, and it's easy to answer questions super quick. Other times they'll give you lists of data values, which you'll have to put in your L1 and L2 to collect information from, but you have both representations here, okay? Keep in mind that sometimes you won't have positive relationships. Sometimes you'll have either a negative relationship that they're trying to find information from or associations with. Sometimes they just think that there is a different relationship, something that is not zero. Okay, so know that a not equal to sign could exist as well. All right, so as we finish, and I kind of wrote over this, I'm embarrassed to say I did this. It says reject the null hypothesis. I'm sorry I didn't answer my question, do step 5, but there it is. Okay. All right, there's your assignments 5, 7, 9, 10, 13, 15, 16, 20. That is 3, 6, there's 9 questions there. All right, and those are the last 9 questions that I'm assigning for your school year with respect to new material from your book. All right, if you have any questions, you let me know. Hope you have a great day.